fun. Okay, so welcome to Math 341. Stat 341, this is probability, this is lecture 3. And so what I want to do today is I want to cover a couple of things. I want to review binomial coefficients. So hopefully everybody has seen binomial coefficients before. You've hopefully seen them either in Algebra 2 or in a pre-calculus class, advanced mathematics class. And then I want to talk a little bit about how to handle some binomial coefficient identities by a technique that I call proof by story. And so frequently when we're trying to do basic combinatorics, the most difficult thing is finding the right way to look at the quantities. It is not easy, but the more things you do, the better you will get at it. This is not a class where you'll be expected to do high-level proofs like this, but this is supposed to be preparing you for moving up to the core classes and whatnot. So I want to introduce stuff like this. I want to talk a little bit about coding efficiency. So how many of you feel very comfortable coding efficiently? Okay, not that many. The more problems you can do, the better. Did I tell you about my student who did not like the extra credit I assigned in probability? So he's a tenured professor of operations research, brilliant student, and he was very upset that I assigned extra credit in probability because he wanted to do the problems, but he didn't have time to do extra credit. If I made it mandatory, he would find the time to do it. And you're William students, you should exactly understand what this is like. You have so many demands on your time, you learn to prioritize. I am not going to assign you mandatory things to do in overwhelming loads. It is up to you to figure out what do you need to do to master the subject to the extent that you want it mastered. If you ever want to do more problems than are assigned, if you ever want to do more practice things, great. The TAs and I are happy to talk to you, but I don't want to make it mandatory because then everyone has to do it. So again, if you want more practice coding, strongly urge you to try to do some more coding. I'll talk a little bit about one of my favorite games, roulette, not to play, but to analyze as a mathematician. And then we should have time today to get into the axioms of probability. So a lot of it is, if you could create the laws of the universe, what would you choose for the laws of probability? And how close are we to what you want? And what do we need to make it rigorous? Is there anybody here who has taken measure theory? Okay, good. So this is what you really need to make everything super rigorous. And so, hello? Okay, that's why I have the phone on. I will try to let you in. Yep. Okay. I'm going to just make them a co-host. So if anybody else comes into the waiting room, please let them in.
Okay.
Okay.
I'll do that. Thank you.
And so, the question is, if you could create your laws of probability, what would you choose? How close are the actual laws of probability to what you want? And what do we need to rigorously prove all of this? This is a first course in probability. I have a friend who believes, that a first course in calculus, calculus of one variable, well, it never said a function of a real variable. And he wants to do, no, that's not what Calc 1 is supposed to be. A first course in probability is not supposed to get into excruciating detail about sigma algebras and all that stuff. There is some stuff about this in the textbook in chapter 2, just so you're aware of what is needed to make it rigorous. So that if you want to, you have an idea of what you would do in later classes. But that is not the goal of this class. For this class, we're basically going to be working with things that we understand. Everybody knows what an interval is. Everybody knows what a rectangular region is. Those are the kinds of events we're going to be looking at. Those are the kinds of things we're going to be assigning probability to. We're not going to be assigning the probability to, we randomly choose a number in 0, 1 such that it doesn't have a 2, 3, or 5 in its binary expansion, or that the fraction of such numbers is no more than 15% as we walk. We're not going to be working with strange sets like that. We'll be working with very nice, well-defined, easily understood stuff. Okay, if you do want a little bit more detail, you can watch one of the lectures from 2019 where we go into a little bit more of the set theory paradoxes and whatnot and stuff like that. And again, whenever I put stuff like this, I will then compensate by taking away some classes as well so that you're not being overloaded with time. Okay. So the first is review of binomial coefficients. So, there we go. So n factorial you read as n factorial is n times n minus 1 dot 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 times 3 times 2 times 1, with 0 factorial defined to be 1. So can somebody tell me in words, is this helping anybody? Or if this screen is not helping anybody, if this screen is fine, all right, yes, I'm going to just raise it so I don't keep walking into it. Wrong one. Yeah, no, wrong one. So can somebody tell me in words what n factorial means? So in words, what would n factorial mean? So somebody in words, what is n factorial? Yes.
It's the product of sequences of integers from.
Okay, but what does it mean? Give me a story. What does n factorial represent? So you've told me how to compute it, but what does it mean? So it's how many arrangements of n objects when order matters. So president is different than vice president, is different than secretary, is different than treasurer. And so we write that with the factorial sign, and we define 0 factorial to be 1. Right? That's just a definition. It seems reasonable. There's one way to do nothing. Okay. Notice we're not defining the factorial for negative integers. We're not defining the factorial for real numbers. We're defining it for non-negative integers. You can extend the factorial to a function that is defined for all real numbers, in fact, even for complex numbers. And we'll get to that later, and we'll see why it's important. And as an aside, for the extension, everyone has already seen this. You get negative 1/2 factorial is the square root of pi. When we extend it, we no longer have the interpretation that this is the number of ways. It doesn't make any sense to talk about how many ways can you arrange negative 1/2 of a person. But there is a function that agrees with the factorial for the non-negative integers and has an extension. The next is the n choose k, which is n factorial over k factorial, n minus k factorial. And you can view this as n factorial over n minus k factorial over k factorial. This is the number of ways to choose k from n when order does not matter. So think of it as we have n people and we're choosing k to be representatives, and all representatives are the same. So much of math comes down to trying to write things in a way that's clear. Why am I writing it like this? Well, n factorial over n minus k factorial, this is n minus 0, n minus 1, dot, 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 n minus k minus 1. Can somebody tell me what that represents? So what would that represent? Yes, to choose k from what? From n when order matters. So you can think of it as, we have n possibilities for the first, n minus 1 for the second, and then n minus k minus 1 for the last. And then why are we dividing by k factorial? Well, this is the number of ways we can choose when order matters. Well, if I have k objects, how many ways can I arrange those k objects? K factorial. So that's why I want to view this as n factorial over n minus k factorial. I'm choosing k objects from n when order matters, and then I'm removing the order. If you have calculators, you might see the NCR, NPR keys. You might remember those from high school. Normally, we do write the binomial coefficients like this. All right. Is this hopefully mostly a review? Okay. So probably one of the most important identities comes from Pascal's triangle. And if I give you x plus y to the n, this is the sum. K goes from 0 to n choose k, x to the k, y to the n minus k, or k goes from 0 to n choose k, x to the n minus k, y to the k. Either way is fine. So this is the binomial theorem. This should be a review. One use is in calculus. The derivative of x to the n, you look at the limit as h goes to 0 of x plus h to the n minus x to the n over h. And we use the binomial theorem to expand things out. So normally you start off with a binomial theorem where the exponent is an integer. You can push and you can extend. If you think about what's going on, the proof, if I give you x plus y to the n, this is x plus y, x plus y, dot, 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 x plus y. I have n factors. When I expand, for each factor, I either choose an x or a y. What's the highest power of x I could get? X to the x. That's a very badly written n. So the highest power of x I could get is x to the n. The highest power of y I could get is y to the n. And you notice that the sum of the exponents of x and y always has to add up to n. If I choose x 5 times, I choose y n minus 5 times. And this is the proof almost by story that as I expand this out, this has to be n choose k, x to the n minus k, y to the k, or x to the k, y to the n minus k. If I choose xk times, I've chosen y n minus k times. So when I'm expanding it out, I have n factors. For each factor, I choose either an x or y. How do we get a term x to the k, y to the n minus k? Take x a total of k times, then have y a total of n minus k times. Now, if you think about this, that's not exactly the binomial coefficient we have. How many ways are there to choose k of the n factors to be x? So how many ways can I choose k of the n factors to be x? So I've got n factors. I want k of them to be x. How many ways? And choose k. So does everyone agree that there's n choose k ways to choose k of the n terms to give me an x? How many terms are left? N minus k. And of those n minus k factors, how many of them have to be y? If I want to get a term x to the k, y to the n minus k, if I choose xk times, how many times do I have to choose y? N minus k. So I have n minus k factors, and I need to get n minus k factors of y. How many ways can I choose n minus k objects from n minus k objects? One, or written in a very fancy way, n minus k choose n minus k. That's really what the coefficient is in front of x to the k, y to the n minus k. But as was remarked, n minus k choose n minus k is just 1. So we would write it like this as n minus k choose n minus k equals 1. But from a story perspective, it's there. And that gives you a better sense of what's going on. It's really a product of binomial coefficients. And this is useful if you want to try to extend to a multinomial. What if I had x plus y plus z to the n? So, again, if you want to try to challenge yourself, do x plus y plus z to the n. Anybody know a good way that you could maybe start to try to understand x plus y plus z to the n? Any thoughts on what we could do? Yes? Yes. And nobody ever groups y and z for some reason. Everybody always groups x and y together. Now, we're in a situation where we can use the binomial theorem. And this is a really important idea. Take something complicated and reduce it to something simpler, something you already know how to understand. And so now we have the binomial theorem that we can use here. And then we're going to have to use the binomial theorem inside the binomial theorem to get x plus y. And then do we get something nice? This will lead to multinomial coefficients. All right. So Pascal's triangle, you've hopefully seen this before. It's all ones on the outside, and then on the inside, it's each number is the sum of the numbers above to the left and above to the right. And so, for instance, 4 is 3 plus 1. 10 is 4 plus 6. Okay. These are the numbers that come from expanding x plus y to the n. This is what we get when we expand x plus y to the n. These are the binomial coefficients. And you have this beautiful relation, n plus 1 choose k plus 1 equals n choose k plus n choose k plus 1. This is an extremely useful identity. How many of you have seen this identity? I mean, this is essentially how Pascal's triangle is created. Each number, n plus 1 choose k plus 1, is the sum of the previous row to the left of it and the previous row to the right of it. So there are lots of ways to prove this. Can somebody give me a brute force way to prove this? Yeah. Expand, right? So proof 1, expand. It's not pleasant, but a lot of the terms are going to be the same. So with a small amount of algebra, it will work out. Proof 2 is story. I need a great school. This shouldn't be a hard question. A great school. No one can think of a great school. Wow. Williams, all right. So we have n people from Williams. Anybody know a school that might not be so great? Amherst. I have one person from Amherst. I want to choose k plus 1 people from these n plus 1. How many ways can I choose k plus 1 people from n plus 1 people? So this is the definition of something we've seen many times today. So this is your chance. If you haven't spoken yet, here's a chance to make a comment. So how many ways can we choose k plus 1 people from n plus 1? Almost. We have n plus 1 people. N plus 1, choose k plus 1. That's the number of ways we can choose k plus 1 people from n plus 1 people. Now, there's two possibilities. We could be in the unfortunate situation that we have someone from Amherst in our group, or we could be in the lucky situation where we don't have someone from Amherst. Are those two cases distinct? Are they disjoint? How many ways can you choose that Amherst person? I'm sorry? 1. How should I write 1? One choose 1. So 1 choose 1. I choose the Amherst. I need to get up to k plus 1 people. I've already chosen one. How many Williams students do I need? K. So how many ways can I choose k Williams students from n Williams students? And choose k. Or we could be in the situation when we don't have the Williams student, the Amherst student. How many ways are there not to choose the Amherst student? I tried. So the Amherst population is just one person. We don't want to choose any of them. I'm sorry, 1 choose 0. 1 choose 0, right? We don't choose the Amherst person. No Amherst. And now how many Williams students do we need? Because we want to get up to k plus 1. We don't have anybody from Amherst. How many do we need from Williams? K plus 1. So it's just going to be n choose k plus 1. And we do a filled in square to indicate the proof is over. So we've just proved Pascal's identity. The reason this works is what does 1 choose 1 equal? 1. What does 1 choose 0 equal? Okay. So this is a proof. When we're writing Pascal's identity, there's really factors of 1 that are hiding there. One of the things I really like about writing it like this is you're less likely to make a mistake when you're doing calculations. How many people are there total? N plus 1. The tops always add up to n plus 1. The bottoms always add up to k plus 1. If you just look at Pascal, you've got n plus 1 on the top on the left, but only n on the right. You have k and k plus 1 on the bottom. By writing it like this, the tops are always adding up to n plus 1. The bottoms are always adding up to k plus 1. Okay, let's do 2 more. Any Dr. Seuss fans here? Any Dr. So I once got into a Dr. Seuss rumble with one of my colleagues when I was a postdoc at Brown. And it wasn't fair because not only did he have kids, he had grandkids. You know, he just had decades over me in terms of reading. So I was able to get through the first quarter of The Cat in the Hat, and he just kept going. Right, so I will not go into Dr. Seuss here, but anybody ever read the Sneetches? Okay, how many types of Sneetches are there?
2.
There are 2 types of Sneetches. What distinguishes the 2 types of Sneetches? No, they're completely different.
Whether it has a star on the belly or not.
What's the difference between the Sneetches?
Some have a star on their belly.
Yes, some of them have a star on their belly and some of them don't. I won't spoil the story for you as to is it better or does it not matter if you have a star or not. Okay, and it may be very similar to, now that I think about it, the Butterball boar. Okay, so imagine you want to choose choose k from n. Order doesn't matter. How many ways can we do that? So by now, everybody should be able to answer this. How many ways can we choose k from n when order doesn't matter? No. And choose k. And choose k. So these, they get the stars. All else get nothing. Okay, so one way of looking at it is I'm going to choose k people and they get stars. Another way of looking at it, and we don't like this as a society, is I'm going to exclude people. How many ways can I choose n minus k people to exclude? Choose n minus k from n. Order doesn't matter. To be excluded. And that's n choose n minus k. And what should be true about these 2 things? They should be the same. So this is a proof by story. You could, of course, go through and do the algebra. Algebra proof. N choose n minus k is n factorial over n minus k factorial n minus k factorial which is n factorial over n minus k factorial, which is n factorial over k factorial, n minus k factorial, which is n choose k. Or do story, count, or counting the same thing. I prefer the proof by story. For this one, you can actually do the algebra without too much trouble. There's a whole slew of things we can prove like this. And if there's more time at the end of the day, I'll show you maybe a few more proofs like this. Okay? So again, if you can find the right way to interpret things, it's not so bad. Okay. I have to be careful because this is being recorded. Has anybody ever listened to Spotify? Does anybody not have the subscription service where you have to hear commercials? Do you ever hear the same commercial in quick succession? In fact, maybe multiple times in quick succession. My son and I are getting very frustrated about one of the gambling ones where they say, if you make a $5 bet, you then get $200 to use in future bets so long as you bet in a certain amount of time. What should you be able to do? So you get you make a $5 bet, and you might lose that, and you get $200. How? Well, but you don't get the $200 until after your first bet. You bet $5, and then after that bet, assume you lose, you then get $200 that you can use on a future bet. What could you do? Good, yes, set up multiple accounts, right? So you and I, well, actually I was at Dartmouth, and so I was talking with some of the Dartmouth Math Club people. We both set up accounts, right? We both put $5 on the same game in opposite directions. We get $200, and then we each put it. This should work, right? So if anybody's interested, we actually want to try this. Now, why do you think they're willing to do this? Yeah, I think we believe that the flaw is they think people will keep betting, that once they have the account, they'll keep betting. So the question is, can mathematicians show restraint? And so if people are interested, shoot me an email, because we'll carefully look at all the legalese to see about this. But it just seems like if you have people taking opposite sides of the bet, just every now and then stuff like this happens. You know, I think I mentioned in the first class that there was a lottery where they doubled the winnings once a month, and people made millions of dollars off of this. Every now and then, people either don't calculate probabilities correctly, or if you can show some restraint, you can actually get in, make a profit, and get out. And so if anybody is interested in stuff like this, let me know. Happy to try to do something like that. Okay? So this opens us up to the world of gambling. You might ask, why are we talking about gambling in a class on probability? A lot of probability was designed to analyze games of chance. Lotteries have often been described as a tax on people who don't know mathematics. Now, there's still a lot of good things that can happen, and for a lot of people, it's worth taking the chance. If I lose, $10 a week, I'm getting entertainment out of this, and if I hit it big, it changes my life. It's worth the risk. So, this is for those of you who are doing economics, a nice expected utility calculation. So we want to analyze various games. And so one of the most common games that people analyze is poker. Right now, I'm not going to go into an analysis of how do you gamble in poker, but there are different types of hands, and different hands are worth more in terms of beating other hands. What do you think makes a hand worth more than another hand? The rarer. So the rarer the hand is, if they define the probabilities correctly, the harder it should be. When you introduce wild cards, there can actually be some flips in terms of which hand is now rarer than another's. Is everybody familiar with the standard deck of 52 cards, 13 cards in each suit? Aces can be high or low. Okay, so here is my first question. What is the probability we have at least 2 kings in a hand of 5 cards? So how would you do this? There's a couple of ways you could do this. Does it matter which order you get the kings? No, we could go through and we could do a very painful thing is maybe I have my kings in the first and second spot, first, second, third, first, second, oh my God, there's so many. No, you don't want to do something like that. Let's just look at how many ways can I choose 5 cards from 52 with at least 2 kings. So how many kings could I have? I could have 4. What else? 3. What else? 2. So I have to look at king, whoops. So I have to look at maybe king, king, star, 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 king, 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 star, star, or king, 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 star, where star is a non-king card. Do I care which suit the king is? No. The biggest issue in probability in doing calculations like this is accidentally double counting. Is it possible if I have 3 kings that I also have 2 kings? What's the probability I have 2 kings if I have a hand with 3 kings? 100%, right? It's happening. Is it possible I could have 3 kings if I have 2 kings? No, I should not be putting it at the board. Is it possible that I could have 3 kings if I tell you my hand has 2 kings? Yes. And so I've got to be very careful. So sometimes people might say, let me look at all the ways I could have the king of spades and the king of hearts. And then let me look at all the ways I could have the king of spades and the king of clubs. Well, that also, I have to be careful about the case when I have the king of spades, the king of hearts, and the king of clubs. There's double counting. And this will lead later today to inclusion, exclusion. How do you handle stuff like this? So how many ways can you choose 5 cards from 52? Yeah, so hopefully we've done this now enough today that when you hear certain words, you understand this is going to be the n choose k, right? So it would be 52 choose 5. So the probability is something over 52 choose 5. How many ways can I have exactly 2 kings? So I have to choose 2 kings. So somebody who hasn't spoken in a while, how many ways can you choose 2 kings from the 4 kings? 4 choose 2. And now, how many cards are left over for my remaining 3? I'm sorry? Well, I'm saying I want a hand with exactly 2 kings. I've chosen 2 kings from the 4. How many cards are left over where I can draw my remaining 3 cards from? I'm sorry? 48. I can't draw from the kings. It's not 50. If I wrote, 50 choose 3, that would be wrong. Because if I do that, I could accidentally choose a king again. So it's not 50 choose 3. Oops. It would be 48 choose 3. Or I could choose 3 kings, and now how many cards are left over? It's still 48. And now how many do I have to choose? Or I could choose all 4 kings, and then I have to choose 1. There's another way to solve this problem. Does anybody know another way to solve this problem? I could do 1 minus. So it's 1 minus the probability I choose no kings, 4 choose 0, 48 choose 5, plus 4 choose 1, 48 choose, I'm sorry, 4 choose 1, 48 choose 4. It doesn't make too much of a difference now, but if we had, say, a game like Bagel where you have 2 decks, and you can now have 8 kings, it would be much better to do it as a 1 minus. So for a lot of problems, it's easy to calculate the probability that something doesn't happen rather than the probability that something does happen. All right. The next one is perhaps one of my favorite problems in all of these poker hands. I want a hand of 5 cards, at least 2 kings at least 2 queens. So what are the possibilities? So what could my hand look like? Two kings, 2 queens, and something else. What else? Somebody else. 2 kings, 3 queens. Anything else? And so star is non-king, non-queen. Does everyone agree that if I wanted to, I could calculate these probabilities? This is not that bad. If it is possible, you should always write a computer program to check. Okay, so I encourage you all to write a computer program to check this. Can somebody talk about what you would do to make a computer program? How would your computer program work? What would it look like? So I want to create a deck, right? And then what do I do from the deck? Randomly sample, right? So I think the phrase is pseudocode, create deck of 52 cards. So what will the elements of my deck be? Numbers. What numbers? So we could do 1 to 52, right? So you could do 1, 2, ... 52. And what are the kings? 2 possibilities. 2 reasonable possibilities. Yes. Good. You could do the first 4 of the kings, or you could do the last 4, right? And then what would be the queens? You could do the second and say 1, 2, 3, 4 a king, 5, 6, 7, 8 a queen. Okay. Then randomly and uniformly choose 5 cards. And now what do you have to do with those 5 cards? So how do you see if it was a success? So how do you check to see if you have 2 kings? So you would have to write some code to check and see, do we have at least 2 of the numbers? 1, 2, 3, 4. Do we have at least 2 of the numbers? Does that sound pleasant? Give me a simple way that you could check. Do I have the first? And if yes, I increase my king counter by 1. Do I have the second? If yes, increase the king counter by 2. So check one at a time to see if 1, 2, 3, 4 is in. If yes, increase the king counter by 1, then do for queen counter. Both must be greater than or equal to 2 for a success. So does everyone agree that this would work? If I changed it and all of a sudden I wanted to consider at least 2 kings, 1 queen, and 1 jack, could you modify the code without too much trouble? That's the advantage of something like this, where we create a deck like this, is this would help us solve a bunch of similar problems. And so if all of a sudden somebody changed their mind and said, no, actually, I want you to do the following. That's fine. I've already created my deck. I can easily accommodate. But what if you know that they're not going to change their mind, that this is the only problem they care about? You have the option of writing different code that will not generalize as well, but is suited specifically for this problem. And so the other possibility is the deck is 10, 10, 10, 10, 1, 1, 1, 1, and then all zeros. And now you see if the sum is what? Not quite. Almost. You just said if the sum is above 22, there's a subtle thing wrong. Can you give me a sum that's greater than 22, but it doesn't have 2 kings and 2 queens?
Oh, above 22 and above, like below, like 32.
But 30 would be 3 kings and no queens.
Oh,
So what should the sum be if I want to have 2 kings and 2 queens at a minimum? But then if I got to something like 40, that would be 4 kings and no queens.
I'm not saying that just as a that is the floor, right?
Yeah.
And then
Yes.
you could mod it.
You could. Or you could, yes. But 30 or 31, they both have. Yeah. Check to see if sum is in what set. Yeah. Just check and see, is my sum one of those 3 numbers? You can do this for Sudoku. Rather than doing the numbers 1, 2, 3, do 1, 10, 100, 1,000, and then just see if the sum of a row is 111,000, 111,000,000, 111,000, 111. If that's the case, you have one of the numbers. So this cuts down on some of the checking you need to do. If this doesn't make sense and you care, ask me. This will solve the problem, but this is a more efficient way of coding. And what it's basically saying is, I don't care about non-kings and non-queens. I only care about kings and queens. I'm going to make the kings 10. I'm going to make the queens 1. And now the only way I can get a number like 22, 23, or 32 is if I have at least 2 kings and at least 2 queens. And so this becomes a really nice way of attacking and coding a problem like this. So I strongly urge you to write both codes. Try to do stuff like this. If you've ever tried to code and learn how to code by just reading a book, not a good idea. Oh yeah. You've got to roll up your sleeves, actually write the code, and become frustrated because you have a small typo somewhere and it's just not working, and you have to spend a lot of time debugging. So I strongly urge you to spend the time to write some code, do problems like this. And then you can write code like this and run it million, billion, trillion times. And you can see if your answer is correct. Later in the semester, we'll get to some more interesting questions where if I try, I think I can sneak something by you in terms of what's the right way to do things and accidentally double count. And how can you tell if I've accidentally double counted something? Simulate, right? You should have as a default, whenever you have a probability question, can I write a code to simulate this? Doesn't matter what language you use, just try to simulate it, okay? And if you can, then you can check and see if the theory is right. It's possible you might have made a coding mistake, and your theory could be right and the code could be wrong, which is really frustrating. But as a rule, I want you to be able to write simple code to get a feel. So do problems like that. If you want more problems, I'm happy to give you some other problems that you can do. Okay, any questions on something like this? So again, you can start to see that there's a lot of cases that you have to consider, and you have to try to figure out what is the best way to do stuff like this. Okay. I think the next thing I said I wanted to do was generating functions. And so generating functions are absolutely wonderful. Now, this is a pre-core class. I am allowed to mention things such as real analysis, measure theory, advanced analysis. I am not allowed to require that you have seen them which means I cannot always prove things rigorously. Okay, so we will sometimes just, we'll just manipulate things. And then in a later class, we will go through and do it very slowly. So I still remember, freshman year, I was taking a wonderful physics class, and my professor said, now, the following step takes about 6 weeks to justify in a math class. Moving on, we see the following. Okay, so anything I am showing you can be justified. Okay, so a lot of times we might have some function f of x is the sum n goes from 0 to infinity of an x to the n, and an is a sequence we care about. And the hope is that maybe we have a closed form expression for f. And then we can use that to deduce information about the ans. So the hope is get a closed form expression for f, use that to deduce things about the ans. Okay? So, or things related to them. So, for example, the Fibonacci numbers, there's a lot of ways to define them. I am the president of the Fibonacci Association, but I am not allowed to change the definition. But I can choose which of the 2 or 3 definitions we use. Today, we will use the definition where f0 is 0, f1 is 1, and fn plus 1 is fn plus fn minus 1. You can form some function g of x to be the sum n goes from 0 to infinity of fn x to the n, and I believe it's something like x over 1 minus x squared. Something like that. And from this, it yields Binet's formula. Fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. This is one of my favorite formulas in all of mathematics. What kind of numbers are the Fibonacci numbers? Positive integers. So imagine you've been assaulted by a number, and there's a police roundup, and you're trying to identify which number did it to you. Does that look like an integer? You've got divisions, you've got square roots, everything works. This is an integer. Not only is it an integer, but 1 minus root 5 over 2 is less than 1 in absolute value. If you're less than 1 in absolute value, what happens is you take a very high power. It goes to 0. So the nth Fibonacci number is the integer that is closest to the first term. This allows you to jump to any Fibonacci number. So as a nice exercise, go through and prove a formula like this. Do not worry about justifying anything you're doing with sequences and series. Anything you want to do, just assume you can do it. So as an extra credit, try to prove something like this. I might have the formula slightly wrong as to what it is. The Binet formula I know I got right. I think it's x over 1 minus x squared. And so see if you can somehow prove something like that. And this is why we care. Now, later in the semester, what do you think the big theorem we're going to look at in 341 is? What would you guess? Central limit theorem, right? In lower classes, we say the fundamental theorem. We say central here. Okay, it's the same thing. This is big. Generating functions become one way of attacking things such as the central limit theorem. And so what I'm trying to do in the beginning of the semester is just plant the flag and have you get a sense of what we're going to be doing. Right now, this is when you're trying to decide which classes do you want to stay with. I want you to get a sense of what we're going to do. We're not going to do things fully rigorously, but I want to put in enough stuff so that if you do want more rigor, you can just let me know, and I'm happy to give you additional stuff. Let's do another fun thing with functions like this. Let's say f of x is 1 plus x squared plus ... Does anybody know what this equals? If instead of using x, if I use the letter r, would that be easier for people? 1 plus r squared plus r cubed. We saw this on the first day of class. Yes.
1 over 1 minus r.
Yes. 1 over 1 minus x here if the absolute value of x is less than 1. One nice proof, and again, I'm not worrying about if things are rigorous, is f of x is 1 plus x times 1 plus x squared plus dot dot dot. I just pull out an x from everything from the second term onward. Well, what is 1 plus x squared? It's just f of x again, right? So I would get f of x is 1 plus x f of x. Therefore, 1 minus x times f of x equals 1. Therefore, f of x is 1 over 1 minus x. So long as everything converges, this is fine. Let's see something interesting about this. So again, let's let f of x be 1 plus x squared plus x cubed plus dot 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 is the sum and goes from 0 to infinity of x to the n is 1 over 1 minus x. And I'm going to apply to both sides the operator d by dx. I'm going to take the derivative. So what happens to the exponent of x if I take a derivative? It decreases. How much does it decrease by? It decreases by 1. So I'm going to take x by dx, and then I'm going to multiply by x so that the power is unchanged. So what does 1 go to when I take the derivative with respect to x and then multiply by x? It's just 0. Or if I want to, I can even view it, I'll do 0. And then what happens with x? What does x go to? 1. What about x squared? What does that go to? I'm sorry? 2x. What about x cubed? 3x squared. So this is the sum and goes from 0 to infinity of n x to the n. And now when you do the algebra on the other side, you got to be a little bit careful because when you take the derivative, it's 1 minus x to the negative 1. I have a negative sign, but then I'm taking the derivative of 1 minus x that gives me another negative sign. And so the negatives reinforce. So I'll let you do the differentiation, but you get x over 1 minus x squared. So for example, if I take x equals 1/2, I will get 0 plus 1 plus 2 over 2 plus 3 over 2 squared plus 4 over 2 cubed plus 5 over 2 to the 4th plus dot 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 equals 1/2 over 1 minus 1/2 squared, which is just 2 when the dust settles. This allowed me to handle, calculating this, strange sum. We used to know how to evaluate things like the geometric series. This allows me to evaluate something related to the geometric series. How many of you have ever seen like the home shopping network where they have these products? And if you're one of the first 100 callers, they throw in something for free. This is essentially what we're getting here. It is a lot of work in mathematics to prove an identity. Identities are the bread and butter of mathematics. We love them. Wouldn't it be wonderful if I had a machine that you put in an identity and it generates new identities for you for free? That's what we're doing here. By differentiating, we created a new identity. After differentiating once, what could we do? Again, you could keep differentiating and you can generate infinitely many new identities from this. So this is an absolutely wonderful technique. Yes?
The way you've written out the sum, isn't it 1
Oh.
plus 1 plus a bunch of other stuff?
Did I make a mistake? Well, I'm taking x equals 1/2. So I mean, the first one I can write is 1 over 2 to the 0, if you want. Did I make a mistake somewhere?
Well,
Or
I guess I'm just saying, like the second and third term are both 1.
yes.
And then there are more positive things added to have that sum.
Oh, did I make a mistake? So did I make a mistake? Group. So excellent that you're doing something like that to do a quick test. So if I take, so I get 1 minus a half, which is 1/2 squared is 1/4. The 4 comes up top. Oh wait a minute. Okay. So wait a minute. I think I might be shifted by 1. Ah, yes, this should be an X, not a 1 here. Thank you. Good. Yes. So that's exactly what you should be doing. You should be checking to see, have I made a mistake? Excellent. And so this should be 1 times x plus 2x squared plus 3x cubed, because it's supposed to be nx to the n. So I was shifted off by 1. So now when I do that, sometimes the best thing to do is to just erase and write it all over again. And that's the best way to make sure you don't make a mistake. So it's going to be 0 plus 1 over 2 plus 2 over 2 squared plus 3 over 2 cubed plus 4 over 2 to the 4th plus dot 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 plus dot dot dot. Perfect. Thank you. Yes. Because I'm multiplying by x. I'm not just taking the derivative. I'm multiplying by x so that the power stays the same.
For the second line, it doesn't have the 1 and more like y, like we don't like minus 1.
What do you mean by the minus 1?
But it doesn't have y, it's 0. It's not 1.
The 0 here?
Yeah.
I mean, I could drop the 0, because when I take the derivative of 1, I just get 0. I don't have to keep writing the 0 if I want. I could just ignore the 0.
So like the other one have like another n, so we write nx to the n.
Right.
It doesn't have that 1, so why don't we minus 1?
Well, so if you look at nx to the n, when n equals 0, you get 0. When n equals 1, you get 1 times x. When n equals 2, you get 2x squared. So that now matches what we have on the left. So this is the same as the sum of nx to the n. If you think about it, if I have x to the n, if I take the derivative, I get nx to the n minus 1. But then I multiply by x, so the x to the n minus 1 becomes an x to the n. And so in some sense, I could start the sum at n equals 1 if I wanted to, because there is not going to be a, the term corresponding to n equals 0 just vanishes. So you've got to be a little bit careful. When I take the derivative, I do lose the constant term. And then when I multiply by x, there's no constant term. Can I add back 0 if I want? Yeah. So let's look at fun definitions. Can somebody tell me what 3 choose 5 should equal? What should 3 choose 5 equal? 0. Why? Why should it be 0? There's no way to choose 5 from 3, right? I've got 3 objects. I want you to choose 5. Order doesn't matter. I don't care if order matters or not. I can't choose 5 distinct objects from 3. Let's look at the definition. 3 choose 5. If we write that as 3 factorial over 5 factorial, 3 minus 5 factorial, what's 3 factorial? 6. What's 5 factorial? 120. So it suggests that -2 factorial is what? What's the only way we could make this equal 0? Not 0. I'm sorry? Infinity. It suggests that the factorials of negative integers. And so I'll just put here, so we'll do more with this later in the semester. The gamma function, gamma of s is the integral from 0 to infinity, e to the negative x, x to the s minus 1 dx. And it turns out gamma of n plus 1 is n factorial if n is a non-negative integer. And gamma of 1/2 is negative 1/2 factorial, I'll put that in quotes, is the square root of pi. So if you've taken a stats class before, anybody know where you've seen a square root of pi? Anybody remember seeing a square root of pi in something in stats? In the Gaussian, yes. The normalization constant for the Gaussian is coming from this. So we'll see later why this is a good definition. We'll see later why it's an why it's an s minus 1. If you were defining something, why would you put an s minus 1? It makes things better. It's not immediately clear. But it's trying to figure out how would you want to define things. If we want to define, n choose k as the number of ways of choosing k objects from n, 3 choose 5 should be 0. And this is suggesting that if I want to extend the definition of the factorial, the only thing that would make sense for negative integers would be to make it equal to infinity. Okay. What I want to do now is ask you for your wish list. Wish list for probability. And again, you've already read the book, so you should have some idea, but we could do maybe wish lists for other subjects. We could do a wish list for calculus. How many of you remember the product rule? This is a prerequisite for the course, so your hand should be up, right? What's the product rule? Good. Good. Plus the first times the derivative of the second. If you were the supreme being and you were creating the laws of calculus, would this be your choice of the product rule? The derivative of a product is the product of the first times the second plus the first times the derivative of the second. I mean, that's going to be a big tablet. What would you choose as your rule? The derivative of a product should be the and what should the derivative of a quotient be? Quotient of the derivatives, right? We have the derivative of a sum is the sum of the derivatives. If you do this, you will be hailed as a just and merciful God. You will be worshipped. Generations of followers will sing praises unto thee. That's not what we have. And it turns out there's good reasons why we don't have the derivative of the product is the product of the derivative. This leads to integration by parts. It allows us to do some interesting things. You don't always get what you want. You don't always get the simple thing. What would you want for the probability of A and B to be? If you could have anything you want, what would you have it? Sure. So this would be really nice. But this can't be true. Give me a choice of B as a function of A where this won't be true. There's a good choice of B.
Complement of A?
Yeah. If B equals A, that implies the probability of A equals twice the probability of A. So all events have 0 probability. Not going to be a very interesting world if every event never happens. So it is too restrictive to have this on our wish list. Can you modify it a little bit? So put a condition on A and B where maybe this should be true. So pairwise disjoint. And since we only have 2 objects, you're saying pairwise, I think you see where this is going, but it is true if A and B are disjoint. So do we want that to be true? Does that seem like a reasonable thing to wish for? And then if we continue with our wishes, what should the probability of A union B union C union ... equal if pairwise disjoint? Pairwise disjoint means that no two sets have any element in common. What would you hope is true? So it'd be the sum of the probabilities, probability of A plus probability of B plus ... Does everybody agree that this would be a wonderful thing to have? Nope. Nope. Not true. Anybody know why this is not true? Well, if A has nothing in common with B, and A has nothing in common with C, and C has nothing in common with B, that's not the issue. There is a subtle issue here. So the danger is uncountable infinities. So I don't want to do too much of this. I just want to plant the flag. How many of you have not seen countable versus uncountable sets? Okay, so it turns out that there are different levels of infinity. There are the integers and the rationals. And these are the countable infinities. It's the smallest infinity there is. Then there are the irrationals and the reals. And this is a large infinity. This is uncountable. What's really strange is there any set with a larger infinity than the integers and a smaller infinity than the reals? It turns out that the existence of such a set is independent of the other axioms of set theory. You can either work in a situation where there is, or you can work in a situation where there is not. One of my mathematical grandfathers is Paul Cohen, the person who finished the analysis of this, and using a new technique he created called forcing. We're not going to worry about any of that, okay? So essentially, the lowest level of infinity is just some set that can be put into a one-to-one correspondence with the integers, A1, A2, A3, A4. An uncountable set can be put into a one-to-one correspondence with either the reals or something larger. And the problem is, if I look at the probability of the union over all x and 0, 1 of the set containing just x, if that were true, then that would be the sum over all x in 0, 1 of the probability of x. If that number is 0, then you get 0. If it's not 0, you would get infinity. And so the problem is there's no way to do this and have something reasonable come out. So pairwise disjoint is not enough. Need more than pairwise disjoint. So we need countable. We need something that can be put into a one-to-one correspondence with the integers. And so just writing things nicely, whenever we have something like a sum over I, you should view this as a finite sum, or say a sum I goes from 0 to infinity. So you would have sets A1, A2, A3, ... We have a nice way of ordering all the sets. Those are the only types of infinity we will look at. We are not going to be looking at uncountable infinities and trying to assign probabilities to stuff like that. The book has a small section on the Banach-Tarski paradox for people who are looking for a truly challenging colloquium. This is a topic that is, typically done at least every few years here. Again, going back to your wish list, if I take an object, should its volume change if I just translate it? Should its volume change if I rotate it? It is possible to take a solid sphere and cut it up into 5 pieces. And you can translate and rotate 3 of the pieces and assemble them into a complete sphere with no gap. And you can take the other 2 pieces, translate and rotate them, and make another complete sphere with no gap. And these 5 sets have no elements in common. If you could do this, what you do is you take a solid sphere of gold, right? Or you take a stack of $100 bills or something like that and apply. And you keep applying. So this involves what's called the uncountable axiom of choice. It involves sets that are so bad we can't describe them. We have to be careful when we do probability that stuff like that can exist. And if you have sets like this, all bets are off. All right. So in this class, we're going to restrict ourselves to sets that you understand. Has anybody ever seen congressional districts, what they look like geographically? Could a kindergartner understand and describe every shape as you go over all congressional? No, right? Yeah. You want nice, simple sets. That's what we're going to study. Rectangles, circles, discrete sets of integers, infinite sets of integers, things like that we'll assign probabilities to. We're not going to be deciding on how should we decide and define probabilities in these more general settings. Just so you know a little bit what's going on, at the high level, we have a triple. We have some space omega, and then sigma is going to be a set of subsets of omega where we will define probability. And then we want our probability function to have a couple of rules that any event that we are allowed to define a probability gets a probability between 0 and 1. The empty set has no probability. The full set has probability 1. And if we have a finite or countable union of disjoint sets, then the probability of the union is the sum of the probabilities. So your wish list works so long as you look at a nice space with nice subsets. And so we're not going to specify in complete detail in this class what is a nice space. This is you'll know it when you hear it, okay? We will only look at stuff like that. A little bit more rigorously, we've done already the probability of a union of 2 sets is the probability of A plus the probability of B minus the probability of the intersection. And you can get this with Venn diagrams. Below is the beginning of inclusion-exclusion is the probability of 3. How could you prove the formula for the probability of 3? And this is similar to something we did earlier today. What could you do? You could group it. So we could look at this as the probability of A1 union A2 union A3. And now we have 2 distinct events. And so as an exercise, use the probability of the union of 2 events to get the probability of the union of 3 events. And then see, how could you generalize that? Can you get a nice formula? What's nice here is it looks like we only have plus and minuses. And it looks like there's some pattern to it. Another one is if A is a subset of B, the probability of A is at most the probability of B. This is the great example of one of the no-shit rules of probability, right? If I have a space that has fewer elements, it should not have greater probability, okay? If one way you can prove this is you can write B as A plus everything in B not in A. So that's what A complement means. The thing's not in A. I'm looking at the intersection of B and A complement. And so you can now prove this by using the fact that the probabilities are between 0 and 1. So as a nice exercise, prove this. And then, lather, rinse, repeat. if I have AI is contained in B, then the probability of the union of AI should not exceed the probability of B. All right, so this is a good place to stop for today. I do want you to do some practice coding.